Okay, now it is audible. Pranay,
Yes, sir.
hello, audible. I think it is audible. Just give me response in chat box. Hello. Okay, now it is audible. Now in the morning we have seen three sensors, that is encoder, rotary encoder, resolver and LVDT. Now we will see another sensors in that. Next is tachometer. Now all of you are using the tachometer, that is it is used for measurement of the speed of the shaft. You are measuring the speed in RPM. Now such sensors can directly find the velocity at any instant of time. This measures the speed of rotation of an element. There are various types of tachometers in use, but a simpler design is based on the Fleming's rule, which states the voltage produced is proportional to the rate of flux linkage. Here, a conductor, basically a coil, is attached to the rotating element, which rotates in a magnetic field, that is stator. As the speed of the shaft increases, the voltage produced at the coil terminals also increases. In other ways, as shown in figure, one can put a magnet on the rotating shaft and a coil on the stator. The voltage produced is proportional to the speed of rotation of the shaft. This information is digitized using an analog to digital converter and passed on to the computer. Therefore, in case of tachometer, here we can use, that is in other ways, we can use a magnet on the rotating shaft and a coil on the stator. The voltage produced is proportional to the speed of rotation of the shaft. Therefore, whatever speed of rotation of the shaft will be there, according to that, this voltage will be produced. Now you see here from north to south, these magnetic flux lines are flowing north to south, and this is ferromagnetic core. Therefore, the voltage produced is proportional to the speed of rotation of the shaft, and this information can be passed to the computer, that is analog information is converted to the digital values. Therefore, this is nothing but the tachometer. Now we'll see its video, small video.
टेकोमीटर एक मेजरिंग डिवाइस होता है जिसका यूज मशीन के रोटेशनल स्पीड और एंगुलर वेलोसिटी को मेजर करने के लिए works on the principle of relative motion between the magnetic field and shaft of the coupled device. There are two types of tachometer: AC tachometer generator and DC tachometer generator. In this video, I will explain about DC tachometer generator. आज की वीडियो अगर आपको लगेगा कि ये चैनल आपके लिए हेल्पफुल है तो प्लीज चैनल को सब्सक्राइब कर ले और बेल आइकन को भी प्रेस कर ले ताकि वीडियोज आप तक पहुंच सके। डीसी टैकोमीटर परमानेंट मैग्नेट, आर्मेचर, ब्रश, कम्यूटेटर, वेरिएबल रेजिस्टर एंड मूविंग कॉइल वोल्टमीटर से मिलकर कंसिस्ट होता है। जिस मशीन के रोटेशनल स्पीड को मेजर करना होता है उसको डीसी टेकोमीटर के शाफ्ट के साथ कपल्ड करते हैं। वर्किंग प्रिंसिपल ऑफ डीसी टेकोमीटर। जब कपल्ड मशीन का शाफ्ट रोटेट करता है तो उसके साथ डीसी टेकोमीटर का जो शाफ्ट है वो भी रोटेट करता है। जब डीसी टेकोमीटर का आर्मेचर रोटेट करेगा तो उसमें ईएमएफ इंड्यूस होता है, बिकॉज जो शाफ्ट है वो परमानेंट मैग्नेट के बीच में प्लेस्ड है एंड जब रोटेट करता है तो प्रोड्यूस होने वाली मैग्नेटिक फ्लक्स को कट करता है। सो फ्रॉम फैराडेज लॉ ऑफ इलेक्ट्रोमैग्नेटिक इंडक्शन, टेकोमीटर के आर्मेचर कंडक्टर में ईएमएफ इंड्यूस होता है। इंड्यूस होने वाला ईएमएफ का मैग्नीट्यूड रोटेटिंग शाफ्ट के ऊपर डिपेंड करता है। मतलब कपल्ड मशीन का शाफ्ट जितना ज्यादा स्पीड से रोटेट करेगा उसके साथ डीसी टेकोमीटर का शाफ्ट भी रोटेट करेगा एंड उतना ही ज्यादा मैग्नेटिक फ्लक्स को कट करेगा। सो magnitude of induced EMF is directly proportional to a speed of shaft. जब आर्मेचर वाइंडिंग में ईएमएफ इंड्यूस होता है तो वो एसी नेचर का होता है, इसलिए वहां पे कम्यूटेटर रिंग का यूज किया जाता है। जो कम्यूटेटर रिंग है वो इंड्यूस्ड एसी करंट को डीसी करंट में कन्वर्ट करता है एंड ब्रश के थ्रू जो आउटपुट रहता है वो मूविंग कॉइल वोल्टमीटर में जाता है एंड जो वोल्टमीटर है वो इंड्यूस्ड वोल्टेज के वैल्यू को मेजर करता है। वहां पर वोल्टमीटर के साथ सीरीज में एक वेरिएबल रेजिस्टेंस कनेक्ट रहता है जो कि वोल्टमीटर में जाने वाली हैवी करंट को कंट्रोल करता है। द ईएमएफ इंड्यूसेस इन डीसी टेकोमीटर जनरेटर is given by E is equal to 5Pn upon 60 into Z by A, where E is the generated voltage, I is the flux per pole in Weber, P is the number of poles, N is a speed in revolution per minute, Z is the number of conductor in armature winding, and A is the number of parallel paths in the armature winding. Here is directly proportional to n. मतलब शाफ्ट का जितना ज्यादा स्पीड ऑफ रोटेशन होगा उतना ज्यादा ईएमएफ इंड्यूस होगा। तो इस तरह से कोई भी टॉपिक को अगर आप इजी वे में समझना चाहते हैं तो चैनल को सब्सक्राइब करें और बेल आइकन।
Okay, now next, Hall effect sensor. Another velocity measuring device is the Hall effect sensor, whose principle is described next. If a flat piece of conductor material called Hall chip is attached to a potential difference, see that this is the Hall chip, it is placed in between north and south poles of the magnet, and that Hall chip is connected to that voltage signal, is attached to a potential difference on its two opposite faces as indicated in figure. Then the voltage across the perpendicular faces is zero. This voltage across the perpendicular faces is zero. But if magnetic field is imposed at right angles to the conductor, we will place magnetic field to the right angle of this conductor or perpendicular to this horizontal surface of the conductor, the voltage is generated on two other perpendicular faces. The voltage will be generated on other two perpendicular faces, means to which these two connectors are there to this Hall chip. Higher the field value, higher the voltage level. Therefore, whatever higher the magnetic flux, higher will be the voltage level. If one provides a ring magnet, the voltage produced is proportional to the speed of rotation of the magnet. Therefore, if you will provide the circular type of magnet, it will be the voltage produced is proportional to the speed of rotation of the magnet. Therefore, this is nothing but Hall effect sensor. Again, I will explain. This is the north and south pole of this permanent magnet. So they can be used to generate magnetic flux. This voltage source is connected. Now you just see in between these two north and south poles, one Hall chip is placed, and that Hall chip is also connected to this EMF or this potential difference to the device which generate EMF or which generates voltage. Now, whenever this magnet will produce magnetic flux, therefore depending upon that voltage level or the values of the voltage will change across the perpendicular faces. Now if this north to south, this magnetic flux line, they are passes. Therefore, what is happening? Voltage is induced in these two opposite faces, which are perpendicular to this horizontal face of this Hall chip. Means this face or this here in this at this point we will get the voltage signal. Therefore, higher the field value, higher is the voltage level. Therefore, this is nothing but the Hall effect sensor, and this Hall chip you can connect it to the object or thing to which we have to measure the velocity or displacement. Therefore, you can get that voltage is directly calibrated in terms of the velocity or in terms of displacement, and we'll get the value. Therefore, this is nothing but the Hall effect sensor. We'll see the videos so that you will understand it better.
Introducing SpeechLog, the most natural sounding text to speech software on the market. Hey, I'm Joey, and I'm one of the 30 AI voices from SpeechLog. You listen to this.
See that chip is placed now in between the magnet, Hall chip. Battery means voltage source. Again, on two opposite faces, voltmeter is there. See that here voltage is given from this battery. So from this battery current supply is there, sorry, and the magnetic field deflects the electrons in the conductor, creating a potential difference. Here you will get voltage, value of the voltage. This current will cut the magnetic flux generated by this magnet. Another video will see. I think same video is there. Therefore, this is nothing but the same video. Sorry. Therefore, this is nothing but the Hall effect sensor, in which Hall chip is placed between the two magnets, and magnetic flux is flowing from north to south. And when that current is passed through this Hall chip, that magnetic flux lines are broken and it induces the voltage here, and we are getting the voltage signal. Therefore, that voltage signal depends upon the value of the magnetic flux, or higher the value of magnetic flux, higher will be the voltage level. Now, next is the strain gauge based sensors. See that a strain gauge is a type of electrical sensor. Its primary use is to measure force or strain. Now already you are knowing that strain is nothing but change in length upon original length. Therefore, the resistance of a strain gauge changes when force is applied, and this will give a different electrical output. Therefore, resistance of the strain gauge changes when force is applied, that we are going to see the animation. Strain gauges use this method to measure pressure, force, weight, and tension. Therefore, strain gauges are used to measure pressure, for pressure measurement, force measurement, or weight measurement, and tension measure. Tension is also one type of force. Therefore, see that here strain gauge is there. This is the strain gauge. Now here electrical wires are connected at the two ends of the strain gauges. This is one end and this is another end. Now this is the gauge baking. This is the resistive foil. Strain gauge consists of these different parts. This is the solder pads. Now strain direction. This is the strain gauge. It may be moved towards right or it may be moved towards left depending upon the force applied. Now these strain gauges are mainly used in Wheatstone Bridge. Therefore, we will see the construction and working of Wheatstone Bridge. Then I will explain how Wheatstone Bridge is used to measure the force in case of cantilever beam when we will apply strain gauges on the cantilever beam. Therefore, this is the cantilever beam with strain gauges. This is a Wheatstone Bridge circuit. First of all, I will explain what is Wheatstone Bridge. Wheatstone Bridge, also known as the resistance bridge, calculates the unknown resistance by balancing two legs of the bridge circuit. One leg includes the component of unknown resistance. Samuel Hunter Christie invented the Wheatstone Bridge in 1833, which Sir Charles Wheatstone later popularized in 1843. The Wheatstone Bridge circuit comprises two known resistors. These four resistors are there: R1, R2, R3, R4, and galvanometer is connected here. And here that voltage source is there, or EMF source or battery. The Wheatstone Bridge circuit comprises two known resistors, one unknown resistor, and one variable resistor connected in the form of a bridge. This bridge is very reliable as it gives accurate measurements. Now, this is nothing but Wheatstone Bridge. Now, construction of a Wheatstone Bridge. Again, same figure is there. I have taken it from Byju's. A Wheatstone Bridge consists of four arms, of which two arms consist of known resistances, and the other arms consist of an unknown resistance and a variable resistance. See that a Wheatstone Bridge has four arms, P, Q, R, S. Two are known resistances, one is unknown and another is variable resistance. See that S is here variable resistance. Means you can decrease resistance of this resistor. That's why it is known as variable resistor. The circuit also consists of a galvanometer and an electromotive force source. See that this electromotive force source means this is battery, and this galvanometer is connected in between here, between the two junctions. The EMF source is attached between points A and B, while the galvanometer is connected to the points C and D. Sorry, here A and here B should be there, and here C and D should be there. Here instead of B, C should be there. Instead of C, here B should be there. The current that flows through the galvanometer depends on the potential difference across it. Therefore, the current flowing through the galvanometer depends on the potential difference across it, and it varies when this variable, we can change this variable resistor. Now this, you are knowing that from this battery we can, therefore with the help of this battery we can pass electric current through this Wheatstone bridge, and that current is divided into I1, I2, I3, and I4. Now, Wheatstone bridge application. The Wheatstone bridge is used for the precise measurement of low resistance. Wheatstone bridge, along with operational amplifier, is used to measure physical parameters such as temperature, light, and strain. Quantities such as impedance, inductance, and capacitance can be measured using variations on the Wheatstone bridge. These are the applications. Now, what are the limitations of the Wheatstone bridge? For low resistance measurement, the resistance of the leads and contacts becomes significant and introduces an error. For high resistance measurement, the measurement presented by the bridge is so large that the galvanometer is insensitive to imbalance. And third, the other drawback is the change in the resistance due to the heating effect of the current through the resistance. Excessive current may even cause permanent change in the value of resistance. Therefore, these are the drawbacks or limitations of the Wheatstone bridge. These are the applications. Now, this video we will see, then you will understand it better.
Good grammar and spelling are important, but if you want to write essays that inspire, messages.
Welcome to another basic electronics video. Today we will take a look over the Wheatstone Bridge, how it works and why we use it. This is a very common and simple circuit based on resistance values used with sensor application. Combine this with an operational amplifier and you will get the good sensing circuit. Before we start, make sure you hit the subscribe button and the notification bell in order to see my future projects. Also, thanks to my patrons for your support. So let's get started. This video is sponsored by GLC PCB, which upgraded their factory so now they can offer 5 pieces of common 2-layer PCBs with a production time of only 24 hours, and that without any additional fees. So for that, prototyping becomes faster than before, but for the same low price. Upload the paper file, select the PCB settings, and order high-quality PCBs for a few dollars. What's up, my friends? Welcome back. Okay, so what is the Wheatstone Bridge? Well, a good definition would be that it is the most common and simplest bridge network used to find resistance values. It uses configuration to detect very small resistance changes and that could be used with sensor applications. We convert resistance changes to voltage changes, and that is very useful. This is the configuration of this bridge. We have 4 resistors in the shape of a diamond. We know the value of 3 resistors, but the 4th one is unknown. The supply voltage is connected to points A and B, and between points C and D, we will later measure the voltage drop, so we need a voltmeter. So here's how this works. Between the points A and B, we have 2 voltage dividers. One divider is made by R1 and R2, and the other one is made by R3 and the unknown resistor. Using the voltage divider formula, we get that the voltage on point C is R2 divided by the sum of R1 and R2 and multiplied by the input voltage. And the voltage on point D is Rx divided by the sum of Rx and R3 and multiplied by the same input voltage. So the voltage drop between C and D is the voltage on C minus the voltage on D, and that is equal to this. But what we are looking for is a balanced bridge, and that is when the voltage between C and D is equal to 0. So if we imply that the voltage CD is equal to 0, we get that the voltage on C is equal to the voltage on D. That means that one divider is equal to the other divider value. So let's clean a little bit this equation. The VE value is on both sides, so we can delete it. Now we cross multiply and we get this. We pass all the Rx elements to one side, and we are left with this. We know that Rx R2 minus R2 Rx is equal to 0. So we get that R2 R3 is equal to Rx R1. So from this we get that the Rx is equal to R3 multiplied by the division between R2 and R1. So why is this important? Well, if R1 and R2 are a constant value, let's say 20 ohms, Rx will be equal to R3 multiplied by a constant value. So by changing the R3 value, we could get that to be equal to the Rx value. And in that way, we have 0 volts between C and D. Okay, so now we know what value of resistor we should have in order to have 0 volts between point C and D. But the Rx is the unknown value. So what we do is to put R1 and R2 to a known value, but we make R3 to be variable. We change the R3 value till the voltage between C and D is 0, and that's when the bridge is balanced. But now let's give some values. On one side we have, let's say, two resistors of 20 ohms, and the supply is 10 volts. Using the divider formula before, we get that the voltage on C is 5 volts. We change the R3 resistance till we get 5 volts as well on point D. Okay, so now let's say that the unknown resistor is a strain measurement gauge. This gauge will increase the resistance under forces. In practice, the range of a strain gauge resistance is from 30 ohms up to 3000 ohms. For a given strain, the resistance change may only be a fraction of the full range. Therefore, to measure a fraction of resistance change with high accuracy, the Wheatstone bridge configuration is used. Right now, the bridge is balanced, so we have CD equal to 0 volts. So now we apply force on the gauge, so the resistance is getting bigger. So the voltage drop on the gauge is now bigger as well. Let's say that the gauge is now 35 ohms. So the voltage on point D would now be 6.36 volts. So the voltage between C and D is negative 1.36 volts. So now we can measure that voltage drop. So we have passed forces measurements to very small resistance changes and then to voltage values. So we could use this into our projects, maybe connected to a microcontroller. But now you might wonder, why not use the gauge directly with the voltage divider? Well, these kind of sensors might change the resistance by other factors as well, as for example by the temperature. Let's say that we apply force on the gauge, and we measure a resistance of 20 ohms in a room of 30 degrees. Then we apply the same force, but in a room of 50 degrees, and now we get 18 ohms. So that means that the gauge read is not reliable, because it will change with the temperature as well, and we don't want that. But if we put this in a Wheatstone bridge together with other resistors that will also change by the temperature, the output won't be affected, because the entire system is affected by the temperature, but only the gauge is affected by the force. So we separated the temperature error from the gauge sensor. We could use this setup with a gauge sensor, a light-dependent resistor, or a thermistor, so we could measure forces, light, or temperature. It is a basic circuit and it is very easy to understand. Okay, so as a short example, I've connected a Wheatstone bridge on my breadboard, and we have two resistors of 100 kilo ohms. Then we have a variable resistor of 200 kilo ohms, and then we have a thermistor that will go up to 200 kilo ohms. Between point C and D, I connect my multimeter and I supply the circuit with 10 volts. I rotate the variable potentiometer till the voltage is 0 volts between point C and D. So right now the bridge is balanced. But now I heat up the thermistor, but as you can see, the voltage is changing, and I could now measure temperature. And the same goes for this LDR, or light-dependent resistor. Below this video, you will find some links to my webpage electromills.com, where you could see all the mathematics step by step, so you could understand more. Also, consider supporting my videos on Patreon. If you enjoyed this video, make sure you subscribe and activate the notification bell for future videos. Also, click the like button like crazy and share this video with your friends. And remember that your help on Patreon means a lot for me, and we'll keep this kind of videos going. So thanks again and see you later, guys.
Okay, this is nothing but your Wheatstone bridge. It can be used to measure force, temperature, and intensity of light. Now we'll see here how this cantilever beam is used, or strain gauges are used to measure the force on the cantilever beam. Now see that this is the cantilever beam. Here R1 and R3 resistances in opposite arms. Similarly, this R2 and R4. These are nothing but strain gauges. R2 and R4 are nothing but the strain gauges. Now you just see you are observing here that this strain gauge deflection, see that contraction and expansion contraction, and this expansion contraction of the strain gauges is directly calibrated in terms of this measuring strain gauge output resistance. Here 1 meter will be there, it can measure the strain gauge resistance. Now you are observing the change in the values also, how these values are changing of the different resistances and how you are getting the voltage here V, that is output voltage. Therefore this output voltage is directly calibrated in terms of force and we are getting the value of the force. Now you just see whenever force will be applied, these strain gauges either they will be in tension or either they will be in compression. Therefore two types of stresses or strains, sorry, two types of stresses are induced, the compression stresses or tensile stresses depending on the type of bending. That is, if now this beam is going in upward direction, therefore compression stresses. If beam is going in the downward direction, tensile stresses are induced in R2 and R4. Therefore you are observing here that the values of the resistances are changing, values of the resistances are changing, and we have used a supply voltage of 10 volt. Here battery is there, it is supplying a voltage of 10 volt, and here galvanometer or voltmeter is there, it will indicate this voltage here. See that whenever it is getting deflected, all four values R1, R2, R3, R4 as well as its final voltage value, it is changing. You can see here also this strain gauge is expanding and contracting. When it is going up, it is expanding. When it is going down, it is contracting. Now therefore this is nothing but the applying varying load on strain gauge, that is use of the strain gauge for measurement of the force. Now next is the piezoelectric based sensor. Now what is the characteristic of that piezoelectric material? Whenever you will apply the force on that piezoelectric material, therefore charge or voltage is produced, and that is directly calibrated in the value of the force, and you are getting the value of the exact value of the force. Therefore a piezoelectric material exhibits a phenomenon known as the piezoelectric effect. This effect states that when asymmetrical elastic crystals are deformed by a force, an electric potential will be developed within the distorted crystal lattice. Therefore, this is the piezoelectric transducer. You just see here on one face, here force is applied so that this piezoelectric crystal or transducer is getting compressed, and depending upon that compression value, that is delta T, that much value of output voltage will be generated. It is a characteristic of piezoelectric crystal, remember. Therefore this effect states that when asymmetrical elastic crystals are deformed by a force, an electrical potential will be developed within the distorted crystal lattice. In opposite, if potential is supplied between the surfaces of the crystal, it will change its physical dimension. That is vice versa. If voltage will supply to this piezoelectric crystal, it will change the dimension of this piezoelectric crystal. That is either it will expand or either it will contract. The magnitude and polarity of the induced charges are proportional to the magnitude and direction of the applied force. The piezoelectric materials are quartz, tourmaline, Rothschild salt, etc. Therefore, these are the different piezoelectric materials: quartz, tourmaline, and Rothschild salt, etc. The range of forces that can be measured using piezoelectric sensors are from 1 to 20 Newton. Now, you will find use of piezoelectric sensors in vibration measurement. That is that accelerometer, one part is there, that in that accelerometer piezoelectric crystal is there. Therefore, whenever machine or system is going to vibrate, and whatever, if we have to measure its vibration of that system or machine or anything, or any type of beam, simply supported cantilever beam or fixed beam or overhanging beam. We have to place that accelerometer on that object, maybe machine or different types of beams, just I have told to you. And if we'll apply exciting force or external force on that machine, you are knowing in the machine force to vibrations are induced because of different cutting forces. Therefore, whenever you will put that object, oh sorry, that accelerometer on the object, therefore that object is vibrating, therefore that at the same time this accelerometer will pick up that vibrations, and through the piezoelectric crystal that voltage is generated, and that voltage is directly calibrated in terms of that vibration values, and you are getting the different different values of the vibrations through this accelerometer. Therefore, in accelerometer, this piezoelectric crystal is there. We'll see the video.
Hi, I'm Clint, and welcome to Autohome. There are many uses for piezoelectrical devices in today's vehicles. We see their effects without a second thought. But can you diagnose a fault with one of these, not knowing how they work? Let's take a closer look at piezoelectricity. A knock sensor is a piezoelectric vibration sensor. When engine detonation occurs, the vibrations are transmitted through the engine block to the sensor. Inside the sensor is a ceramic sensing disc. Vibrations from the detonation put pressure on the ceramic that is proportional to the knock. The ceramic generates a voltage based on this pressure and is sent to the PCM for conversion and interpretation. With a scope attached to the sensor, any substantial vibrations will be detected and reflected as an alternating current signal. These sensors are signal generators, and as such, they don't require a reference voltage to operate. The main reason for using piezo technology is because of its accuracy and reliability. In this air conditioning pressure sensor, we were able to read very small changes in refrigerant pressure by amplifying the signal. This is a sample of the hundreds of training videos we have available, covering everything from technical fundamentals, diagnostic procedures, equipment, and wiring diagrams. Automate is simply the best training available. So why not join us today? Start training and be the best technician you can be.
Okay, this is nothing but piezoelectric sensor which is used to measure vibrations. Now, next is the limit switch sensor. Now, limit switches already you are knowing. Limit switches are there on the milling machine, or you can put it on the lathe machine so that you can restrict the travel of the table in case of milling machine, or you can restrict the travel of the carriage in case of lathe machine. Therefore, a limit switch is constructed much as the ordinary light switch used at homes and offices. It has the same on-off characteristics. The limit switch usually has a pressure sensitive mechanical arm. When an object applies pressure on the mechanical arm, the switch is energized. An object might have an attached magnet that causes a contact to rise and close when the object passes over the arm. Limit switches are used in robots to detect the extreme positions of the motions, whatever I have told in case of milling machine and lathe machine, where the link reaching an extreme position switches off the corresponding actuator, thus safeguarding any possible damage to the mechanical structure of the robot. Therefore, limit switches limits the travel of the robot arm or the travel in case of machine. Now we'll see this video of the limit switch.
question. What would happen?
Okay, this limit switch is there.
In this video, we're going to introduce you to a device called the limit switch. There's probably not a day that goes by where you don't use or encounter a limit switch at home or at your workplace. There are 4 general types of limit switches: whisker, roller, lever, and plunger. Depending on the application, a limit switch may be a combination of 2 of the general types, such as roller lever. Okay, let's get started. A limit switch is an electromechanical device operated by a physical force applied to it by an object. The limit switch is used to detect the presence or absence of an object. These switches originally used to define the limit of travel of an object, and as a result, they were named limit switch. When you open the fridge door, a light comes on inside. How does that happen? Yes, you guessed it. A limit switch is used to detect if the fridge door is open or closed. Let's look at another application of a limit switch that you may encounter at home. On many overhead garage doors, there is a limit switch that stops the movement of the door when it reaches its fully open position. All right, now that we've looked at a couple of limit switch applications where you might see them in action at home, let's have a closer look at the device itself. A limit switch is an electromechanical device consisting of an actuator mechanically linked to an electrical switch. When an object contacts the actuator, the switch will operate, causing an electrical connection to make or break. Limit switches are available in several switch configurations: normally open, normally closed, or one of each. Depending on the origin of the electrical schematic, you may see limit switches drawn in different ways. The International Electrotechnical Commission, or IEC, and the National Electrical Manufacturers Association, or NEMA, have slightly different symbols. Let's have a look inside a micro switch that is a type of limit switch. A micro switch has 2 limit switches operating together and sharing a common terminal. One limit switch is normally open and the other is normally closed. To be technically correct, the switch configuration is single pole double throw, or commonly referred to as SPDT. The dashed line indicates that both switches are mechanically connected and will operate at the same time. All right, let's connect the micro switch to a lamp circuit. In the inactive state, the red lamp is on as the device is not being operated by an object pushing on the trigger. When the trigger is pushed, the device will activate, and the green lamp will come on. Now that you've seen the limit switch in action, you are probably thinking about some of the applications where you have seen them in action. For example, you might see a limit switch operated by a container on an assembly line, or operated by a rotating machine part, or by any number of other moving mechanical objects. A limit switch could be used to count passing objects, or determining the position of a hydraulic cylinder. Limit switches are slowly starting to disappear from many industrial applications. They are being replaced by proximity sensors. Unlike a limit switch, a proximity sensor has no mechanical moving parts. A proximity sensor performs the switching action with electronic switches. Limit switches will not completely disappear anytime soon, as they outshine their proximity switch counterpart in their ruggedness and reliable operation in difficult environments. Generally speaking, limit switches are capable of handling much higher current values than proximity sensors. If you want to learn more about proximity sensors and other types of sensors, check out our other video called "What is a Sensor? Different Types of Sensors, Applications." You can find the link to this video in the description. Okay, let's review what we've covered in this video. There are 4 general types of limit switches: whisker, roller, lever, and plunger. A limit switch is an electromechanical device operated by a physical force applied to it by an object. A limit switch is an electromechanical device consisting of an actuator mechanically linked to an electrical switch. Limit switches are available in several switch configurations, normally open, normally closed, or one of each. Depending on the origin of the electrical schematic, you may see limit switches drawn in different ways. Limit switches are being replaced by proximity sensors in many applications. Want to learn PLC programming in an easy to understand format?
Okay, this is nothing but limit switch sensor. Now next is pneumatic switch sensors. I think time is over. These pneumatic switch sensors we'll see tomorrow. Proximity sensor, limit switch sensors. Now we'll stop here. Thank you very much. Let me note down your numbers. Please don't leave. I will stop recording now.